Okay, my friends, another shocker du jour. They are coming around to dipole electron flood theory. This is Sabine Hoffensfelder. She won't communicate to me. I've been trying for years to get through her, and not a single response. However, she's talking about cold fusion. Here's how it works. Well, it doesn't work when you go into the atomic range where you're breaking up big particles. It takes more energy to break them up than you get back when they come back together. We have a process that we don't have to do anything to break up the particles. They break up all by themselves because we funnel them down into a little gate that's so small that only the energy can get through. The mass pops back. All right, I'll show you. All right, before we can do anything, we got to understand fusion. Well, what is fusion? It means two things added together. Well, they have something where they have like a heavy item. It has too much stuff to begin with. When it adds to another item, it's supposed to give off a bunch of these little particles that are the energy, which are the dipole electrons, basically. And that is what they're looking for, is to be able to break up these big things into little things, and then when they come back together, there's a bunch of extra little things left over. That's what fusion is, and the little things left over are supposed to be their energy. Well, there's another way of doing fusion, and that's the way we did it. And we did it because before you can have fusion, you have to have fission. Well, what's fission? Fission means you got to break these things apart. All right, so you got two balls like this, and you got to slam them and smash them to bits and break them apart. That's called fission. So they just go flying everywhere. Then when they come back together, there's some leftovers because they were heavy particles to begin with. They had too much to begin with. So they didn't want some of that stuff, but now that they come back together, they can give it up. I hope that makes sense to you. Fusion can only happen after you have fission. So you have to break it, and then when it comes back together, that's when you get your release of energy, the excess. Well, we did this. Well, let me show you how we did it. All right, let's just get a little deeper before I show you how we did this. They're talking about using pulsed lasers to bombard different types of metals until they can force particles to come off, and then hopefully they come back together and give off some energy. That's the fusion. But they've never done it. They've never even been able to break even, because it takes a hell of a lot of energy to break into these big particles. Now, we used light, so we were down here, and they were up here smashing huge things together, and they don't hit correctly when they try. There's all kinds of problems by using huge things, and these super colliders are just gigantic, tons of billions and billions of dollars, when you can do this for a couple $100. I'm not kidding you. So let's just go a little further. I'm not kidding you, I'm serious. All right, I'm going to show you what Sabine has to say about fission and fusion and so forth. But you got to start with fission to come back to fusion. This is what particles of light are. They're glued together, and I mean they are glued tougher than tough. You can't get these apart without creating like lightning or electricity or static. Those are when you break the white away from the black. That's what we want, is this white energy. Now, I talked about fission and fusion. This is a particle. It is a particle of light. It's the green ones and the red ones, the blue ones are all the same. Now, this is when it's in its normal configuration. We accelerated that particle and exploded it at the Venturi, which caused fission, and it came back together as fusion. Remember, they were together. The black didn't go through with the white. The white went through, the black didn't. There's more black over here waiting to jump in. There's a lot of extra black laying around. So the white was separated, fission. It came back together, that's fusion. That's what they want to do. And they don't realize that this is where they're going to end up, is here, at this level. They think they got huge things, so they break apart these pieces and they get a chunk like this. No, they're going to get a ton of these little bitty particles, just like we do. And that's what causes the energy, is this brilliance. The brilliance is the energy. Just look it up. High luminosity experiments now they're doing at CERN. They stopped doing all that. Well, I don't know if they stopped. But the proton stuff is huge. It's just a waste of time. Huge amounts of money. Dangerous, expensive, wasteful. This, now they've gone down to the light stuff. They're down in the light range now, and they're going to be doing the same kind of experiments where they're using photon colliders. All right, this is all brand new, these photon colliders. They were using proton colliders before. And here's what they did. Look at this. All right, here's the deal. This was CERN and Fermilab. They wanted to get down to electron showers, which is just what I showed you, those white. So they hit protons. Boom! And they get huge numbers, large numbers of hadrons, which are just chunks, along this beam. Now they have to decay the hadrons to create flux of high energy neutrinos. Now, once you get the neutrinos and the anti-neutrinos, well, that's just up and down. I don't know why they say anti-neutrinos. There is no anti-neutrinos in this mess. They're all neutrinos. One of them's black and one of them's white, if that's what they're talking about. Which is, if they're anti-neutrinos. They're talking about electron neutrinos and muon neutrinos, yes. But there is no anti-neutrinos. Well, you call them whatever you want. Now, the energy of these particular neutrinos interacting with their receiver is 100 giga electron volts, a few hundred of giga electron volts, up to trillions of electron volts. That is enormous, because it only takes mega electron volts to create the initial energy, and you're up to 100 giga electron. That's just an unbelievable increase in energy. But I believe that's exactly what would happen if you could split the white away for free. And we can split it away for no charge whatsoever. And here it is happening before your very eyes. That is light coming forward in a wave, and the particle is in the wave. That's the particle-wave duality. It's being accelerated because a venturi is here, which forces the fields in. It's just like the nozzle on a hose. The hose comes out and dribbles out until you put the whole nozzle on. That's what you got here. And the black bounces back, so you got fission. And the black comes back, you got fusion. All the things they're looking for. In the middle, you got raw energy. And if that's the case, and it does the type of energy increase they're talking about, a device like this, you could power your house, your car, go out in the woods, live in the woods, you could camp out, you could put out fight fires and pump water with it, this anything. Because the increase in energy would be astronomical. Just insane. If it's true, and I can see we did it, slept right in the light, there's no question that happened. This started out as a regular wave. Let me show you and now you know that this is Fermilab. This was from Fermilab, from an article Don Lincoln did at Fermilab back in 2012, 2013. And I saw these particles and I said, wow, these are the same particles we found. The black one with the glowy edge around it and the white one, they see them separated as things that they don't fully understand, but they know they're the smallest particles they've ever seen. So, and I believe they are the smallest particles that existed, we can find. But they're normally glued together. And now they do know this. This is 2013, so this goes back a while. And now they call them gluons, the black and the white. Now, at this point, I contacted Don Lincoln. I said, Don, we found your particles when we put light, which is photons, through a venturi. And boy, that did not go well, and it still is not going well. And he's spending all of our money, and and he's got me blocked. I can't. And this goes back 10 years. We could have maybe had free energy for 10 years. That's the particle. There's the electron showers. This is exactly what they want. Fission, fusion, electron showers, muon neutrinos, electron neutrinos. The muon goes sterile, the black one. The electron goes into shower mode, the big white stuff. Before, they were both tagged together like this. And the reason this one's glowing is because it's moving through the air this way. That one's behind the black particle, so it's not concussing with other fields. This one's glowing because everybody else got a field in front of it. It's got to push them through. And that's why you get all these big, well, I don't know if you can even see that. You see the little dots in front of that thing? See the little red spots? Those are fields. You see all the dust? That's dust. Now, so we got fields, we got dust. Now, this one's growing big, and as it gets a little further, it's going to go whoop, and this one's going to come in the front and start to charge up. That's what's called a muon wobble, and that's what they do. And it split, and it came back together. So, as far as I'm concerned, we already did fission and fusion. We did it 10 years ago. And Don Lincoln is the guy. He said, oh, that's the guy you got to show, and he won't look. And this has happened to me in every single spot in medicine, in everywhere, in medicine, in mud fossils, physics, history, everything. Total refusal to engage by the ones that make the rules, the ones that we have to engage with, because they're the guy. I call it the guy syndrome, or the person, because maybe it'll be a woman now. There's a woman at Yale University. Let's find out if she can handle it. Nobody else could. And this is not going to end well, I can tell you that. Yale has stood in front of my research for over 10 years, 12, more than that, and denied reality, and that's just not going to, at some point, it's going to catch up with them, and I'm hoping this is the point. So, and because this won't be accepted over there either. Not a thing, zero, nobody. And I'm talking every university, not just Yale. Yale's the worst of the worst, but it's not just them. So if we had this right here, and we had this in a box like this, just like this is that box, where you had a ton of these lasers in there, dozens of them, hundreds of them, thousands of them. They're tiny, there's thousands of them. You could have them on strips. You could have them like this. Hold on. You have them on strips like this. You'd have the laser on one side, you have the receiver on the other side. Now, you have to use perovskite, something with transition metal receivers, so that you could absorb all the frequencies of light. And all it is it's the length of the light. Well, actually, if you're using lasers, now that I'm thinking about it, if you're using lasers, you're only going to be hitting it with one frequency of light, primarily. This is something that coming through the Venturi, it might interfere and give you all the frequencies, because it comes out brilliant white, and normally brilliant white is all frequencies at once. So don't forget, we got the laser going through the Venturi, coming out the other side, and we pump it right down into the battery. You don't have to do hardly anything to it, and just then put regulators and all that stuff, a floating ground and all that stuff, and you're good to go. But you could have thousands of these, literally, I mean, because they're tiny. These are huge compared to what you really need. And if the amount of space you need to absorb electrons is just unbelievably small. Think about a little tiny battery. These little, look at this. Here's button batteries. You see these things? One of those tiny little batteries can power something for years. Another device, you know that there's electrons running through all the time. How many electrons are in one of these things? It's just staggering how many electrons can exist in a space. Because these batteries, they're just continuously feeding out the electrons, and they're under pressure. And at a certain point, so many of them go on that the pressure stops, and that's when it doesn't provide the energy enough to push the things that it has to push. And that's what happens in an electric circuit. Your electricity comes down, it pushes a device, and it makes it turn, or it heats it up. There's resistance. Something resists that flow of electricity, or that's called a dead short. If you have a dead short, the wire burns up. Everything burns up. But the resistance is there in a motor, in a heating resistor type thing, where there's a a rod that starts glowing, that type of thing, lights, anything, any device that creates resistance. And you have to have the right regulation, have the right voltage to drive that, and of course the right amperage. You know, there's a lot of little stuff. And whether it's DC or AC, most of it's going to be DC. And anyway, you don't have to know any of that stuff. But I can't see why this shouldn't be looked at. And I really think it's a disgrace what Don Lincoln did to the American people and to science. You know, it's very upsetting, and I don't mean to be this way, but what can I say? Now that was the light, it's a pulsed red laser. So every pulse has a particle in the middle of it. A little tiny particle, it just sits right there. And it has to go through the air. And when it does, everybody else in the air has fields around it. These are all gases and things in the air, but they still have a magnetic field around them, because once you create particles and molecules, they have fields around them. They don't normally interact with each other. They bounce off of each other unless they're for some reason attracted to each other, where they have the different polarities that intermingle, or you add some enzymes or chemistry or acids or salts that break up little bits and pieces off them, and then they hook together. Light just bumps. Light goes around, bump, 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 bump. But a plant will absorb it and eat it. And sometimes it will hit, well, always basically, some of it will hit things, and those things will absorb those particles just for the moment. They're not going to keep them forever, but they'll absorb them as warmth. All right, and then they will just give them off when somebody else wants them more than them. That's how the interaction of particles work. It's a very simple process, it really is. And you have to understand dipole electron flood theory. You don't understand dipole electron flood theory, you're never, ever, 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 ever going to understand anything. Nothing. These are the only two particles that exist. And we are made of those two particles, and everything there is made of. And they can be separated, as I showed you. That's the fission. When they come back together, that's the fusion. And then when they go in photon phase, that they're glued together. This is heat. This is electricity by itself. Total electricity, lightning static electricity. When it's attached to the black, and only one of them, it's heat. That's all it is heat. And when you put two of these together in a form, they turn into light. Light will bounce. This will attach as heat. It'll go into something as warmth, or it'll bounce back, you know, that type of thing. It'll want to incorporate with something. Sometimes it will go in and attach and never leave. It depends. If there's a particle in there that has this, he says, I'd like to get an electron in here, and it finds this guy, and they become stable. There's a lot of chemistry going on. It's just that life is chemistry. The earth is chemistry. Everything is chemistry. And space is saturated with chemistry. And it's saturated with life. All right, now I think I've shown a pretty good display of what has to be seen to understand really about this cold fusion and cold, you know, you got to have fission to get fusion. I just showed you. I think we did it. Well, I know we did it. That light was together here, and it's fission here, fusion there. And I don't know if I have any green up here. Here's a green, the same particle. You see the green? Same particle, only much faster. And this one's getting ready to spin right now. See how it's glowing here, and it's sort of fuzzy looking? How clean looking here it is. It's just getting ready to go. Look. And the red is the same way. And here's the red, like this, coming straight across here. And the red is here. See, now this one's the down spin, the white is down. This one's an up spin, the white is up. And they're both, they're all going in this direction. That's where the Venturi is. Now, I've shown this many times, and this is the way light spins. It doesn't flap like a wave, it spins. Now, this is another thing I want to show you, because this is the weirdest thing. Well, first of all, these are Higgs fields. We can produce these in huge quantities. Nobody's ever seen these before. We're the only one that can show them. You look at it and you say, show me a Higgs field. They said, they don't exist. Nobody can show it. Well, I can. There they are. And now look at this one. Here's the crazy one. We had a backward spinner. Now watch this. You see this? Those are those Higgs fields. Now, here's the Venturi coming in our face. All right, he's got the cell phone right here. In here is just white. That's where that white stuff is. There's no fields. Out here, the black is starting to incorporate it into the white. That one there is spinning backwards. Let me come in close on that so you can really get some detail here. You see that white one? You see how glowy that sucker is? And it's spinning backwards. That's my estimation. It took me 3 years to figure this out. If I got it right. Now, I don't know, but I think I do. And so now, what happens? They're all supposed to be spinning this way. This one's spinning backwards. There's something called a right-hand rule. If the particle is going in this direction, it's supposed to be spinning this way. Right-hand rule. Now, this one here is going in that direction, but it's spinning the other direction. So your fingers are broken off. Now, so what happened to it? Well, his fingers got broken off. Watch. Okay, my friends, this is really bizarre. This is what we use. This is the Samsung Galaxy S3 cell phone and the Bosch laser. This goes back to 2012. And it uses CMOS, complementary metal oxide silicate semiconductors. And then there's amplifiers in every single pixel. And all it's made to do is to receive some form of energy. And then the amplifiers pump the energy up to display. So a little tiny bit of energy, you still see the energy. A lot of energy, you see glowing. It's doing its job magnificently, and it does not interfere with the thing, because otherwise the light would just go by and go somewhere out in the woods. We're sitting off here picking that light up, and this is all we use to do these experiments. That is it right there. And then a little Venturi, which is done with the most simple device. I'll explain that later, because it's so simple that I find it very hard to believe. Now, we saw that white particle coming this way. I believe this is that white particle. Now, what happened to that white particle? It's spinning backwards. These are, this one here, and all the rest of them are spinning in this direction. And you say, well, Roger, how do you know that? Well, because this one's spinning in the opposite direction. All right, it's spinning this way. This one's spinning this way. This one is spinning this way. And you say, well, big deal. What are you showing me? Well, here's what I'm showing you. I says it ripped its fingers off. That's its fingers right there. It appears that the particle, or something to do with the particle, sits at the very tip and somehow forces the field inward, so that you get these ripples going inward. It's what it looks like to me, because this particle, apparently it was sitting right on the outside edge of that reverse field. So what happened? This one's spinning the way it should. This one's spinning backwards. This field grabbed a hold of this field and spun it like crazy right off the side. And this one just kept going. Well, this one didn't keep going, it just stopped. It ripped its fingers right off, it's gone. It ripped it right out of here, so the field no longer exists. And it twisted it. You see how it's twisting here? Can you see all these things? Yeah, it's ripped right off the side, and it's making this little tiny jobber. So, I don't know what to think. This took me years. I looked at that thing basically every day. I said, how the hell did that happen? And that's, so I would say that's a antiparticle turned maybe into a particle. Because it's spinning this direction, and I just grabbed it and ripped it off this way. Well, I don't know. It's hard to say. I know it would. If it hit it, it would spin it back this way. And I think it is. So it's still going backwards. It's supposed to go this direction. And if it hit it this way, it would turn itself backwards. So it's still going backwards, I think. I don't know. It's the only one I've ever seen like that. And I've seen more pictures of these things than anybody in the entire world. Guaranteed. I got hundreds and hundreds and hundreds of them. And some of them are just, well, you can see they're stunning. And they're just made with almost nothing. And Rod Warren in Australia did 99% of this. There's nobody could beat Rod. There is zero anybody anywhere that could beat Rod at this. Nobody. And he worked tirelessly for years with nothing to show for it. And eventually, you know, you walk away. You say, it's just... Anyway, there's the muon neutrino, electron neutrino, muon sterile, electron shower. Seen it? You've seen it, you've seen it, you've seen it, you've seen it. Somebody should step up. This is just insanity. To be blocked from Fermilab just because of Don Lincoln. I want Trump to stand up, Musk, everybody. I want somebody to do something. This is absolutely insanity. And it's not just there, it's everywhere. It's so depressing, my friends. I love you all. Anyway, step up and talk out. You know, this is crazy. The money that they are spending could be used for homeless people, could be used for the people in California, the people in Florida, Virginia, everywhere. All these disasters, we're all in it together. But it's not that way in academia. They're in it for themselves, and that's it. They tell you what to say, and you better say it, or they will pull the rug right on from you and ruin your life and keep your money. And if you don't go there, then you're not educated. You're just not a thinker. You're just not worthy of a good job. They got you coming going. There's no stopping it until Trump stops it, because nobody else can stop it. And I don't know if he can get in there either. But I'm ready to help him. I got the evidence, and I'm ready. And I got other people that are ready too. So I love you all. See if we can get through to somebody. I am blocked. My emails and so forth go out as spam and dangerous. I'm not kidding you. They come with a big red thing on it, say dangerous something, and then there's another big yellow one that comes out with spam. And this is, I don't know if I ever get through to anybody. So, because I never get anything back. So that's my complaint again for today. Hopefully, after the inauguration, and Trump has a little time. You know, we'll see what happens. You know, truth social, truth, that's all I hear. Let's see if we can get some. We need some. All right, I love you all.